times. Deja vu is killing me. But this is in response to a really, really good question that I've been dying to answer because folks have been asking me De Morgan's rule. What is that? Is that true? How do we prove that? How come Hurley just throws it out there without like explaining it? I don't know why. I wouldn't write my logic textbook that way, but I also wouldn't write a logic textbook because that seems boring. Anyway, so there are two ways to prove De Morgan's rule that we've already studied. We're going to go through both of them, hopefully, in this video. The first, it makes use of Venn diagrams. And you can see here, I might have told you, I don't really like drawing Venn diagrams. Why? Because I don't draw good circles. This, like, freaks me out. So what I'm going to do is illustrate these different propositions using the Venn diagrams. And I'm actually going to shade in the parts that are indicated. Normally in Venn diagrams, we shade in the parts that are empty. But I'm just not sure how high quality this image is going to be, and I'm worried that you won't be able to see it if I use X's. I think shading is going to work better. So first, just for practice or for demonstration, we're going to do these really simple propositions, A and B, as we know that describes only those portions of the diagram that are in both the A and the B circles. We'll also do A or B. This is the good old inclusive OR. So that includes everything that is A, and it also includes everything that is B. Why do we do this? Well, because it makes super easy to show what the negation of A and B looks like. It's just everything, and that includes everything outside of these circles that is not shaded in that very first diagram. Okay. So it's this Marquise shape in the middle. And here, once again, all we have to do is color in all the parts that are not shaded in our first image, which makes this butt shape. I'm sorry, I have a toddler. She would have thought that was really funny. She thinks butts are super funny. You are adults, and you probably think it looks dumb because it was. All right. So finally, let's shade in not A or not B. As you remember, this is an inclusive OR. That means in this diagram we want to shade in everything that is not A. And we also want to shade in everything that is not B. What's left unshaded? It's that same Marquise shape in the middle. So this is one way of demonstrating that these two propositions actually say the same thing. They're logically equivalent. Why? Because they describe the same worlds. Finally, we have not A and not B. Okay, so I'm going to start by shading everything that is not part of that A circle. I'll use these vertical lines. Let's take a drawing class that had a whole segment on shading things in. Apparently, I didn't do super well at that. Didn't really stick. Okay, now we're going to shade in everything that is not B. And includes our A circle. Now remember, when we have an and or a conjunction, we need everything that is both not A and not B. And that's only the cross-hatched areas, right? So this part doesn't count. That's not A. No, excuse me, that's not B, but it is A. Whatever. We only want the cross-hatched areas, right? We want things that are both not A and not B. And what are we left with? Well, that same abstract geometrical shape from the negation of A or B. Okay? So these images are one way of demonstrating De Morgan's rule, demonstrating that not parentheses A or B, close parentheses, is logically equivalent and describes the same thing as not A and not B. Okay? And also that the negation of A and B is the same as not A or not B. This is one way of thinking about it, in a way that has used up a lot of my whiteboard markers. All right, and this is the third time I've done that on the board today, so this thing is going to be gray by the time we're finished. Aye. Feels like some CrossFit exercise for professors, like whatever muscle that is, it's going to work out. Okay, there is another way to prove De Morgan's rule, and that uses truth tables. Now, okay, so if you've covered the Venn diagrams but not the truth tables yet, stop, come back to this after you've done 6.3, 6.2, 6.2, I'm sorry, you know, the one with the truth tables for longer propositions. That's going to be 6.3, sorry. If you have already done that, or you're coming back to me after having done so, let's compare some statements. We'll compare not A and B to not A or not B. And then we will compare not A or B to not A and not B. So we're going to create these extended truth tables to compare them. Once again, we are going to need additional columns for both A and B. And for those, for our first variable A, we fill in true, true, false, false. Then for B, we fill in true, false, true, false. We're going to fill in those same values under every A and B. So A goes true, true, false, false, true, true, false, false. Always do all the A's before you start on the B's. Now B's are true, false, true, false, true, false, true, false. Finally, well, not finally, no, this is just the next step. We're going to apply all our negations. And the negation just reverses whatever truth value we have. And we're going to cross out the old ones to avoid confusion. Okay, what's next? Well, we can just do this one, right? And we know that with our nice inclusive or, the only way that is false is if the variables on both sides are false. All the rest of these will be true, and we can draw our rectangle around them. Okay, now we're going to start inside the parentheses on this side. And that's really easy because A and B, that's a really simple basic proposition that hopefully you've already been memorizing. And we should know that that's true only if both A and B are true. We'll draw a rounded bubble around that because we have yet to apply our main operator, which is simply a negation that's going to reverse all these two chickies. We compare the content of those two square brackets, and in both cases, false, true, true, true. Look at that, they have exactly the same truth values, and that is how we know that they are logically equivalent. Logically equivalent, they say exactly the same thing, so we can use them in exactly the same way. Let's do the same thing for these next two statements. And yay, now my neighbor's mowing the lawn. Okay, true, true, false, false for A, true, false, true, false for B. We'll fill in all the A's, true, true, false, false, true, true, false, false. I've done this so many times today, it feels truly insane. For B, true, false, true, false, true, false, True, false, it's Groundhog Day. We have to reverse them. True, true, false, false becomes false, false, true, true. True, false becomes false, true. So we have now applied those negations. Okay, conjunction, we know that is only true when both sides are true. All the others will be false. Okay, bar, rectangle. Okay, we've got an or. We know that is only false when both sides are false. All the rest of them are true. Rounded bubble, because we've yet to apply our main operator, which is simply going to reverse them all. Okay, now we compare our rectangles, and in both cases, false, 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 and true. These are also equivalent. So there you have it, 2 different ways of proving De Morgan's rule.